So if you have read the syllabus today, I was supposed to talk about chasing convex bodies and convex functions. But because Doigu and Pepe, they joined force to have kind of a comprehensive survey about the topics, I decided to give them more flexibility. So I'm not gonna talk about that. So we should wait for their presentation to learn about this beautiful line of work. Instead, I'm gonna talk about actually a problem that I personally think is more applied and kind of relevant to the intersection of computer science and OR. And I personally, in my grad school life, have seen or maybe reviewed 10 papers that in some sense they were a special case of the problem I'm gonna tell you about, but the authors hadn't noticed that it's a special case, maybe because they never learned this paper. So it's a very general problem, has a lot of applications in online auctions, dynamic procurement, display ads, even designing auto biddings these days. So we're gonna talk about it. It's called Bandits with knapsacks. And let me first tell you what are the topics we are gonna talk about today. So we are gonna almost all the time talk about the bandits with knapsacks. BWK. So I'm going to start by the basic setting, tell you what's the most general form of this problem. Then we are going to spend some time talking about the applications, how we can cast different applications in market design and OR into this model. So when we get there, I'm going to tell you the list of the applications and discuss each of them separately. Then we are going to talk about LP relaxation of this problem and how that LP relaxation will lead to what I call a Lagrangian game. This is another reason that I switched the topic today to this paper. I want to put some lecture, maybe just even like one complete class on learning in games. But because of the limited time, we never had the chance to do that. That was one of the bonus lectures that I promised myself to do if we decide to not have presentations during week 9. But because we are going to have presentations during week 9, so I didn't have the chance to talk about learning in games. So I decided to change the analysis of the algorithm for this problem to talk about actually how different online learning algorithms play a game. So we are going to think about a stochastic two-player zero-sum game. And the two players in that game are going to run learning algorithms, and we will see how that will help us to design an algorithm for the bandit with knapsack problem. So after this, there will be a little bit of detour about learning in games. And in particular, I'm going to talk about stochastic zero-sum games. Then we will see how this analysis, when two players in a zero-sum game run learning algorithms, can give you a Primal-dual algorithm for the bandit knapsack problem. And we finish the analysis essentially by putting the different pieces that we have generated during the class together. So that's roughly the plan. So let's just start from the first one, the basic setting. So it's a fairly general model. Let me explain the following language. So in this problem, we have k different arms. What does the arm represent? It will be clear when we talk about the application. We have k different arms. We have d resources. And then we have a finite time horizon t. All right. So each resource I has a budget or a capacity. Has a capacity equal to BI. And for reasons that will be clear soon, without loss of generality, we are going to assume that for every I, all the BIs are equal to each other, are equal to B. You will see soon why this is without loss of generality. All right. So now there will be a game, time t equal to 1 all the way to capital T. And then for each time t equal to 1 all the way to equal to 1 to all the way to stopping. I'm going to tell you when do we stop. The algorithm selects an arm denoted by A of t, so it's going to be one of the numbers 1 to k. We allow randomized algorithms in most general settings. You should imagine that the selection of the algorithm is a point in the k-dimensional simplex. Then given the arm, an outcome is going to be revealed. An outcome is revealed. So the outcome is denoted by O of t. And you should really think of the outcome to have two different parts. So the first part is the reward, and the second part is how much this choice is consuming each of the different resources. So we are going to have RT of AT as basically the reward that you get when arm AT is pulled. And then the second part of the outcome would be, let's say CT1 AT, CT2 AT, all the way to CT All right. So how should we think of these outcomes? Outcomes are generated stochastically. So imagine we have an outcome distribution f of A for each arm I, for each arm A. So what does that mean? So if I look at one particular arm A and I sample an outcome from that arm, so then I'm going to have an outcome O, let's denote it by R, C1 all the way to CB, that will be realized from the distribution f of A. And these distributions are unknown. So what do these numbers represent? So this is going to be the reward. And if you look at CJ here, or CI, so this is going to be the consumption of resource I. So if you pull this arm, then you get this amount of reward, and then from each resource I, you're going to consume CI amount, which will be subtracted from the initial capacity B. And now you can see why this is without loss of generality to assume all the budgets are equal to each other, because I can just normalize things given the consumption factors. And if the budgets are different, I just take the normalization factor into consideration when I think about the consumption.
Can I assume it's on? Oh, right.
No, so because we're going to think about, so here we have essentially kind of like integral allocations. And well, so in some sense you can, but what I care about is the ratio between the budget and T. So you can't normalize everything, but you can normalize each in some sense. So here I assume everything is in 0, 1. So a vector such as O is going to be a vector in D plus 1 dimensional unit hyperplane. So we don't know the distribution. And then there is also the IID assumption. Let me write it somewhere. So the IID assumption. So outcome generated by the same R A or IID draws from distribution. That means if I pull an arm at some time, I get an outcome. If I pull the same arm at another time, I get another outcome. These two outcomes are going to be independent and identical. So all the outcomes corresponding to the same arm that are drawn throughout time are going to be IID draws from the same distribution. Okay. So the goal of the decision maker, so the goal is to maximize the total reward until termination or until stopping. When does an algorithm stop? So an algorithm stops if either t is equal to t plus 1, meaning that you have passed the horizon, or the consumption of one of the resources, or the total consumption, let's say, total consumption of some resource I exceeds this capacity. And in fact, you can even think of time as another resource that is in your control. Imagine you have one resource, its initial capacity is equal to T. The consumption of that resource for all the arms is equal to 1. So that resource is essentially time. So you can really define this problem in a way that there is no notion of time. There are K arms, there are D resources. At each time you pull an arm, you consume each of these resources by some amount. And then there is one resource called time, when the consumption of that resource in every single time for every single arm is exactly equal to 1. And the initial amount of that resource is equal to T, so that will be the finite horizon version. Yes.
Could you repeat why to that lesson?
Yeah.
The normalization stuff?
Yeah, good. So why this is the terminal generation?
Yeah.
Right. So imagine that different PIs are different. Then when you pull some arm A and the consumption is, let's say, CTI, then imagine that in your head that the actual consumption, imagine in your head that the budget is B and the actual consumption is CTI times BI divided by B, right? P over BI, P over BI. Imagine in your head, this is how much of this thing is consumed. It's like I'm multiplying the board by the same factor, which is B over BI, so that the budget becomes B and the consumption becomes. Yes.
You mean we change the FA distribution? Yeah.
I mean, we don't know FA distribution, but every time that you realize an outcome, you get to see the consumptions and the reward as the algorithm. So in that moment, you can normalize things by the factor B over BI for the consumption of each resource. You don't know FA. So if you know FA, the problem is kind of easy. If you don't know the FA, then there is a learning aspect, and this is exactly what we're going to have.
Why the ratio is the only thing matter? For example, if there are some kind of variance or this kind of things that are gonna show up in the computation? Is the ratio the only thing that matters for?
The two problems are equivalent. So in the actual problem instance, the budget is equal to BI. In the fictional problem instance you solve in your head, the budgets are V. The way that you translate the algorithm from this word to that word is just whenever resource I is consumed with the consumption amount of CTI, you multiply that by V over V.
So
Yes.
what do you assume are integers?
Only K, D, and T. Yeah. The rest can be any number.
So the C's may not be integers.
Right. They may not be integers.
But if it's the case, why B being integer matter?
B's can also be non-integers. I think I only need K, D, and T. I didn't say B is an integer. So B is not an integer. K, D, and T are integers. I think if you're referring to my answer to Faro's question.
Yeah.
So all I said was, well, so B divided by T matters. So you cannot normalize both B and T. Yeah. You can assume that budgets are equal to 1, but let's keep them as B. It's just easier to think about it because I can keep track of where the budget appears versus and just escalate.
I think when you assume O is there, you can't normalize B any further.
I mean, yes and no. If I normalize things by B, then I have to normalize this range by B as well. And then things would have been equivalent.
Because eventually you want to assume B over T is a constant or something like this.
No, actually, if you're gonna solve the problem for all the ratios. But the results are more interesting when B is closer to T. When B is smaller than T, the algorithm I'm gonna show you today is not performing very well. However, there are other algorithms. So if B is smaller than T and opt is small, this algorithm is not going to be performing very well. I haven't even told you about the algorithm, but the algorithm I'm talking about is not performing well, but there is a version of that which has the multiplicative approximation, and that one is going to perform pretty well. So many of these questions are going to be clear once I get to the algorithm and the results. Any questions about the setting? Yes.
And right now, when you do that normalization, you don't have to change that about the support for
This one?
the equivalence. Yeah.
I can just normalize by the maximum budget. This has nothing to do with this assumption. So basically, imagine that my basic model is when there is all of them they have in fact, so let's say all of them already have the same budget. I think I probably don't understand your question. When I do this normalization, I don't care about this number to be between 0 and 1. So all I care about is the original number to be between 0. Maybe.
But the setting you have written here, if all PIs are equal to B, so I guess you're using the fact that the consumption that is gonna deduce from the resources is at most 1 at each step. I guess you're going to use this fact.
We are going to use that fact, but you will see in a second it's not important. In fact, I'm using a more refined upper bound line. Just wait a minute, and many of these questions are going to be answered. I guess your concern is after I multiply by B over BI, then this new consumption factor is not necessarily between 0 and 1, then it's going to be between 0 and B over BI. If that helps, just assume it is between 0 and B over BI, but it's not going to matter. Because in the definition of the Lagrangian game, I'm normalizing appropriately, so everything is going to be in the range that I want. All right. Good. So let me tell you some of the applications of this model. And in fact, you have already seen one of those applications. So the first application is what I call dynamic pricing with limited supply. And we spent an entire lecture on this, right? With limited supply. So here the question is, I'm selling, let's say, k units of an item, and each time I'm setting a price, there will be IID sequence of buyers with IID willingness to pay or valuations, and my goal is to maximize my revenue without exceeding the sum. So there we can think of each price P as an arm. And always think about time in these applications as one resource you have and the consumption of that resource is equal to 1. Then I can say with this view, the outcome for price P at time T is basically equal to. So two cases might happen. Either the price gets accepted or gets rejected. So if it gets accepted, then my reward is equal to P. My consumption of the resource is going to be equal to 1, and my consumption of the time resource is going to be equal to 1. So this is the consumption of the supply. This is the consumption of time. And this happens if the value at that time is greater or equal than the price. And otherwise, this is going to be, my reward is going to be 0. I'm not going to consume the supply, but I still move forward for 1 unit, so there is a consumption 1. So you can cast this problem easily as a bandit knapsack problem. Let me give you another example. So it is what I call dynamic procurement. So suppose I'm a crowdsourcing platform. My goal is to hire workforce. So I put offers in front of arriving people who are interested to do the job. Each person has a private type, which is a cost that they have in order to conduct the job. So if the cost is smaller than the offer that they provide, then they're going to take the offer, otherwise they're going to leave it. And my goal is to, and then I have a limited budget for how much money I'm going to pay to hire the workforce. My goal is to maximize the number of people that I'm hiring within my budget. So budget P on hiring. So maximize the number of hires. All right. And then we can say for each offer P, we have an R. Then if I look at the outcome of offer P at time T, again, two things can happen. So if the offer gets accepted, which is the case that my offer is beating the internal cost, this is the cost of worker T for the project that I'm assigning that worker to. If P is greater than the cost, then my reward is going to be 1 because I get 1 worker. How much my budget is going to be consumed by P amount, and then time is going to be consumed by 1. So it's going to be 1 P1. So this is for my budget, this is for time. And otherwise, this is going to be. Let me tell you another example. Is the example clear?
Time should be 1 for the,
Sorry, what?
in the otherwise case. Time is still 1.
This is 0, 0. So another example. let's call that ad allocation. So imagine I'm on an advertising platform, there are different advertisers, each one has a budget. For the purpose of this example, imagine there are two advertisers. First one has budget V1, second one has budget V2. So at each time, a new user arrives to my platform, and I'm gonna, and imagine I have just one ad source. So I'm gonna pick the ad corresponding to one of these advertisers and show it to the user. So the ad is gonna be either clicked or not, depending on the advertiser instruction. So ad of this advertiser, let's say, has some unknown. So this is the unknown part. So it has an unknown click probability. Equals to Q1, this has an unknown click probability equal to Q2. So I don't know these two numbers. And then, okay, so you have essentially an arm for each of the two choices. One and two. Now we can say the outcome of one at time t, for example. So if the user clicks, on the ad of advertiser one, let's say my goal is to maximize the revenue I collect. And also imagine that each advertiser has a price per click. I should have mentioned that. So P1, P2 are the price per click for each advertiser. So price per click one and price per click two. So if you get a click from the ad corresponding to advertiser one, advertiser one is going to pay P1. If it is advertiser two, it's going to pay P2. So therefore, if the user clicks on the ad of advertiser one, my reward is going to be equal to P1. I'm going to use the budget of advertiser one by P1. Budget of advertiser two is not going to be consumed, 0, and we use 1 minute of time. Otherwise, if there will be no click, then you make no revenue, no budget will be exhausted or consumed by any amount, and 1 minute of time is going to be used. So this is budget of this consumption of budget of advertiser one, which is B1, and this is for B2. Let me give you one final example, which is now the gain from the perspective of an advertiser. So this is what I call designing an auto bidder. In today's advertising platforms, like let's say Google, advertisers, they actually ask Google to bid on their behalf in the auction. And now they basically run a learning algorithm to learn how to bid in that auction. So the question is, as an advertiser, given the historical data, how much do you bid in the next auction that Google is running? And maybe you run an algorithm by yourself, or maybe actually trust the company to use an algorithm, an automated algorithm to bid in their own auction. In either cases, your goal is to learn how to bid. And now this is how you should think of it. As an advertiser, I have, let's say, a daily budget. B. For each possible bid, there is an arm. So you have an arm for each possible bid. There should be an appropriate discretization, so on and so forth, but assume there is a discrete set of possibilities, so you have one arm for each possible bid. So your goal as an advertiser is maybe to win the maximum number of auctions. So your goal is to, let's say, win maximum number of auctions. You can imagine different goals as well, but this is one very basic goal. In some sense, you want to win in maximum number of auctions. You want your app to be shown as much as possible. And now when you think about it, as you want to cast it as an example of Bandits with knapsacks, so how the outcome is defined. So the outcome for bid B at time t. So it is the random variable or random vector that really depends on the bids of the other competitor in the auction, right? And you can just model it in this way. So you can say, and also the auction, right? So the part of the outcome is how much your budget is going to be exhausted. So it depends on the auction rule and how much the other bidders are bidding in the auction. We can just imagine everything else except your bid is an exogenous process. And then thinking of it in that way, I would say my outcome would be the reward is going to be 1. I'm going to consume my budget by B amount, and time is going to move forward by 1. Actually, I'm going to consume my budget by, let's say, PT amount, and time is going to move forward by 1 if B wins the auction and payment in the auction, basically payment for the winner, which potentially might be a function of other bids, is equal to PT. Otherwise, you lose, and imagine that you're attending an auction in which no loser pays, then you get 0, 0, and 1. And by the way, this is not always the case. We were having lunch with Avrin Blom, and he was telling us about the all-pay auction in which you might be a loser and still pay. Imagine this is not an all-pay auction. This is an auction in which a loser doesn't pay. Yes, sir.
Where do you see those, like all pay auctions?
Good question. So I think in the example that he mentioned was not really an auction. It was about different candidates in an election. They are putting effort into their campaigns, and eventually the one that who puts the maximum effort is going to win. The highest bidder in some sense is going to win, but everyone pays.
So the lottery amount, the win probability is proportional to the amount of tickets you buy. You can think of that essentially. Is a proxy.
Yeah, that's a proxy to all pay. Good point. But just one thing I want to mention is that the only assumption we are making in order to cast this as a bandit with knapsack is that the set of the buyers that are arriving, or the set of the competing bids are IAD. As long as the set of competing bids are IAD, meaning that you're competing with the same set of bidders as stochastically speaking, then there is some distribution, some leaky back distribution between these two outcomes. You don't know what that distribution is. I don't care, we're going to learn. And then the problem can be cast as an instance of bandit with knapsacks. You see, like this PT is not even a parameter related to your bid. It's just given bid B and given the other players bid, then there will be a random variable PT which determines how much you're going to pay. I put it here in my outcome. This is a very, very general model. And I encourage you to think about other applications of this very, very basic model. But these are the ones that I wanted to definitely discuss. Any questions about the setting and the application? So let's now talk about actually some benchmark for this problem. All right, so two benchmarks. Suppose you know the underlying distributions f of a, basically you know that this outcome distribution corresponding to each r. Then given this knowledge, you can actually find an algorithm that maximizes the expected result. Or in other words, you can think of an algorithm for bandit with knapsack problem that is feasible, and then you can think about the optimum online algorithm given the knowledge about the distribution. Or in other words, you can think about the best online algorithm, right? So optimum online policy that's equivalent to best algorithm for bandit with knapsack given the distribution is f of a. And by best, what I really mean is the one that maximizes, let's say, the expected reward. Or you can think of any other benchmark that you want and pick the best algorithm in that based on that benchmark, but the benchmark should be somehow related to the total reward. So it should be either the expectation of the total reward, it should be maybe you're thinking about the algorithm that the distribution of the total reward has the highest median, things of this sort. So you can always think of any wiki algorithm, but the easy one is the one online algorithm that maximizes the expected total reward. So this is going to be optimum online, but this is not the benchmark we're going to work with because it is hard to compare any algorithm directly with optimum online. So instead of that, as you have seen several times in this course, we are going to work with what kind of benchmark? Any guess?
Optimal offline.
Optimal offline, and usually when we think about optimal offline, we also think about another relaxation of that, right? And what is that relaxation? You have seen that relaxation several times, the previous course and this course. In the dynamic pricing problem with limited supply. So we have optimal offline. Optimal offline should satisfy all the constraint 0.5. But we also think about the
Hires.
Satisfying with what the expectation.
Right, satisfying constraint with expectation, the example relaxation, right? So this is going to be the benchmark we're going to work with, the example relaxation, which is some sort of optimum offline that only satisfies constraints in expectation. I'm going to formally define this example relaxation. Usually in this course, we try to characterize the example relaxation using a linear program. This is why we usually call it example relaxation.p. And this is actually a kind of object that usually it is easier to work with and design algorithms based on that. This is exactly what we're going to do. So let me define this object. First, let me do the following. Suppose D is a distribution over arms. So it is a distribution over arms, which is basically delta K. Then I'm going to define R of D. So this is the definition. So this is going to be equal to sum over all arms D of A, which is the property that arm A is claimed, multiplied by R of A. And what is R of A? So R of A is defined to be the expectation of random variables. So let's say you pick one time. They are IID, so it doesn't matter. Pick some time t. So look at the expectation of RTA when RTA when my outcome at this time is realized from distribution A. So I'm looking at some particular time t. Imagine that you pull arm A, then the expected reward you get is going to be called R. It's the expectation of random variable RTA when outcome is realized from distribution F. And then RD is essentially the expected reward when you realize an arm from distribution. Let's do the same thing with the consumption. So I'm going to define consumption for resource I at arm A to be equal to the expectation of CTIA when the outcome at that time, OT, is realized from distribution F of A. So these are definitions. And then given this definition, we can define Ci of a distribution D to be essentially sum over all i's, dA Ci of A. Yes?
What is DA? Like D is distribution over R?
Arms, or we have k arms, think of D as a k dimensional vector, sum of dA's is equal to 1. So basically, this is equivalent to summation of dA's over all arms is equal to 1, and dA's are greater or equal than 0. And you have k arms. Okay. So with these definitions, I can define an LP. So what is my linear program? The example relaxation. So opt LP is defined to be a linear program in which you're trying to maximize R of t, or R of t, such that first of all, D is in the k-dimensional simplex. And then I have a constraint for every resource. So for every resource I want to have T times Ci of T to be no more than B. All right, so very simple linear program. First of all, is it clear why this is a linear program? What the decision variables are? So the decision variables are k numbers, D A1 for each arm k, arm 1 to k, right? And then these are all linear functions, so this defines it. It's just like bad, not a bad notation, it's a succinct notation. Let me have a question. We seem to have a question.
Do we ever think about our actions kind of like changing things?
Our actions changing things, you mean changing
Like
the
the underlying
distribution?
like that?
No, not in this case. So the underlying, so it's a very stationary model. So the underlying distribution remains the same. If you think about those kinds of models, then you have to starting with MDPs with unknown parameters, which goes into the realm of reinforcement learning. So we are not going to talk about reinforcement learning in this course. We are just thinking about a stationary problem when there is really no state that determines the future distribution. Any other questions? All right, so first lemma, this is a relaxation. What does that mean? So lemma, pick your favorite algorithm, let's say optimum online. So opt online in terms of expected reward is going to be no more than t times octave. And let's try to prove this. This is not actually that. Suppose I look at, consider running optimal line on this instance. Let's define a random variable, I call it xt of a, to be the indicator that at time t, the algorithm indicator that opt online selects arm A at time t. All right. So these are the indicator random variables that you can get once you run the algorithm on this. Now, let's actually think about the reward that the algorithm gets. So reward of the algorithm, reward of opt online in this case, would be sum over all the times, t from 1 to t. And because of the indicator property, I can say this is actually equal to sum over all arms. Xt a times RTA. This is a realized reward of the all of these guys are randomized. The XTA is the indicator that the algorithm selects arm A. RTA is the realized reward when the algorithm selects arm A. Okay. Just multiplying this by t, dividing this by t. If I take expectation, I can say the expectation of the reward of the optimal line is equal to t times summation a in k, and then we have expectation of the average frequency of playing arm A, 1 over t, sum over all t's, xt a times RTA. But then there is a randomness in RTA, which is independent from everything else. So if I look at some time t and some arm A, and I look at the realization of reward for that arm, the randomness that creates this reward is independent from every other randomness in the problem. That means, thinking of this as a random variable and this as another random variable, these two are independent. So this is going to be equal to t summation a in k, expectation of 1 over t, sum over t, xt a, whatever this thing is, I don't care. And then expectation of RTA will be equal to RA. That's the definition that we have here. All right. So now, given the optimal line, I'm going to create a feasible solution for this linear program. So D, which is equal to expected average frequency of playing different arms. So D of A to be equal to the expectation of 1 over t, sum over all the t's xta for every a. So think of it as a distribution. This is actually a distribution, right? Because the algorithm is going to pick only one arm at a time. So therefore, sum of the DAs is going to be equal to 1. So think of this as a distribution. So given optimal line, you can create this distribution. And I claim that 1, the expected reward of optimal line, as we saw up there, is equal to summation or t times summation over all the arms D of A times R of A. This is exactly what we showed up there. And then second, I'm going to show that D is feasible in that LP. So we are going to show T times Ci of D is at most B. So let's try to show this part. It's pretty similar to this step. Proof of this claim. Proof. So we look at our algorithms. Optimum one line creates a feasible solution, point-based feasible solution. So that means for every resource I, if I look at sum over T from 1 to capital T, sum over all A's, XTA, and then I multiply that by the consumption of resource I at time T when arm A is put, then this quantity is going to be at most B. Because we have an algorithm that is going to stop, or it's not going to pull arm A anymore, if pulling arm A causes the budget to exceed, causes the consumption to exceed the budget. Yes, sir. That's fine. If you're wondering why I have the capital T up there, note the definition of XTA, which is this indicator. So automatically, so you never actually exceed any capacity, even if I sum over all the times starting from 1 all the way to capital T. The algorithm by definition is going to stop using, so the first time that it exceeds the capacity of one of the resources is going to stop. And after that, all the XTAs are going to 0. And because of that, you have this inequality. Yes.
So because the algorithm can stop sooner than time T, so why we need that constraint T times GIT less than B? Why? I guess.
Why? I mean, because even though
I think even that cannot be possible in some cases.
no, so mathematically speaking, I'm going to show you given any algorithm they have a feasible solution for this. That part is if you're asking what's the intuition that they have T on the left hand side of that constraint. So the reason is somehow you expect the optimal algorithm to behave in a stationary fashion. So you don't want the optimal line algorithm to exhaust your resources at some certain time more than another time. If you knew the distribution and you only wanted to satisfy this constraint expectation, then somehow you wanted to have a uniform consumption rate of your resource throughout time. That means, so that means, what's that?
I don't understand why that's the case. Why we need that stationary one. Stationary is the optimal.
Oh, because input is coming by ADT. So there is really no difference between time 1 and time 10. Something that you use at time 1, you could alternatively use it at time 10. So if you give me any algorithm that uses the resource at the rate that is changing over time, I can always come up with another algorithm that has a uniform rate of consumption and performs as well as the previous.
Suppose all consumptions are equal to 1. No.
All consumptions are equal to 1.
And they're in the distribution F, they are all realized from very deterministic. And B is, for example, 2, T is 10. How you are gonna make that feasible?
That D will be 1/5, right? Capital D will be 1/5.
Capital what?
Capital D will be 1/5, 1/5.
You can, so this distribution can be basically, so most of the time you don't pick any R.
Oh, so it's, you can.
Oh, maybe I should have.
No R.
Right, yes, right. So there is, okay, this is a good point. So if this is the cause of the confusion, imagine you have a null arm, so you can always pull that null arm and let the time to skip. If this is the source of the confusion. Because in all these applications, you can either post the infinite price or you can go with an offer that never be accepted. So that is the notion of that's the equivalent of skipping the time. So yeah, so we have a null arm. We have a null arm. Yeah, I should have mentioned it. Let me actually write it down somewhere. So there always exists an arm, it's called the null arm. So no reward, no consumption. Only time moves forward. Because if you don't have such an arm, the moment that you exceed one of the capacity and you're forcing yourself to pull an arm, if the consumptions are non-zero, then you're gonna violate the capacity constraint.
Yeah.
So because of that, I assume that you also assume such an array, but maybe I should have mentioned. Right. So back to our proof. So we know 0.5 is the capacity constraint is not going to get violated. Now, similar to the other proof, I'm going to multiply things by t and divide by t. So we will have t times, let's say, sum over a, sum over t's, xta divided by t times ct ia is at most b. Now, if I take expectation from both hand sides, again, because of the independence of this random variable and this random variable, and the fact that the expectation of this variable doesn't depend on t, we're going to get taking expectation. Expectation. So we are going to get t times summation over all i's. Expectation of sum over t xta divided by t times ci of a is at most b, and this is basically t times ci of d at most b. All right. So definitely this distribution is going to be feasible, and then the expected demand of the optimal is going to be equal to the objective. Hence, the LP is a relaxation. Therefore, opt LP is going to be equal to, it's going to be greater or equal than t times the opt LP is going to be greater or equal than opt, as you want. All right. So far, so good. We are going to work with that LP, and every time that you see a LP that has a constraint, the first thing that comes to mind is trying to do you have questions?
Scribe?
Oh, who is going to scribe? We already had discussed. Yeah, we discussed that in my office, right? Excellent. And I actually have very neat handwritten notes, so I can share them with you if that helps. This is one of the rare lectures I have handwritten notes for. Okay, good. So now the next step is trying to design an algorithm based on this LP. So the main idea is, hey, we have this linear program, which is a relaxation. We don't know the solution of the linear program because if you want to know the solution, you need to know the distributions. Otherwise, you can't find RA and CID. So these are quantities that depend on those unknown distributions. But then you might be able to learn the optimum solution of the linear program. So our goal is to design an algorithm that learns the optimum solution of this linear program, and therefore, by mimicking that optimum solution, will give you the good algorithm for bandits with knapsacks that has a small regret map. We know from the theory of linear programming that the optimum solution for the linear program is equal to the optimum solution for its Lagrangian relaxation. And the good thing about Lagrangian relaxation is you don't need to be worried about the constraints. So let's actually do that. So I'm gonna think about the Lagrangian function of the linear program. In some sense, it is partial Lagrangian, so I'm not going to Lagrangiify all the constraints. In particular, I'm not going to Lagrangiify these constraints, I'm only Lagrangiify these constraints. And let me define that. So I'm going to define the Lagrangian function with two sets of variables d and lambda to be equal to Rd. Right, so what I'm going to do next, so I'm going to multiply each of these guys by some lambda I. Actually, before that, let's move this b here. So we're going to have t over b, and this becomes 1. So I'm going to multiply this by lambda I, multiply the right-hand side minus the left-hand side, and I'm going to bring that to the objective. So the Lagrangian function is going to be Rd plus sum over all resources I, lambda I, multiplied by 1 minus t over b times ci of t. That's the Lagrangian function. Good. So a few properties of the Lagrangian function. I'm not going to show them. This is a strong duality. I assume that you know. So strong duality for linear programs. So property number 1. If I look at the max min problem and I'm maximizing over all the probability distribution over different arms and I'm minimizing over all lambda greater or equal than 0, the Lagrangian function, then you can swap the mean and max. This is going to be also equal to the mean lambda greater or equal than 0, max d delta k, lambda d and lambda. And there is a pair of choices, d star and lambda star, such that this quantity is equal to lambda d star and lambda star. There are different ways of interpreting d star and lambda star. So d star is the optimum primal solution, lambda star is the optimum dual solution of the linear program, as we have seen before. Another way to think about that, this is a two-player zero-sum game, where one player is trying to maximize the payoff, the other one is trying to minimize the payoff, and this is the Nash equilibrium of that game. The pair d star lambdas. So I assume you're familiar with this, so I'm not gonna show this, but this is very important property. I'm gonna use it several times. And then we have complementary slackness, which says that, well, so for every I, either lambda I star is 0, or I know lambda I star is greater than 0, and the corresponding constraint is tight. Meaning that 1 minus t over e c I d star is going to be equal to 0. Just one other observation, which I think is kind of important, is that suppose you know d star. So you know the optimal solution from the primal player. So you know the optimum solution of the LP d star. And then from the perspective of d star, if you know d star, how would you pick a lambda that minimizes the Lagrangian function? I'm imagining a situation that the primal player goes first, picks d star, the dual player goes second. Now it's gonna pick a solution that minimizes the Lagrangian. So how would you choose your Lagrangian function? Given the fact that you know d star is feasible, meaning that 1 minus tb cid star is greater or equal than 0. How would you pick the lambda?
Everything else than the maximum of that should be 0, and
Let's write down that. So suppose b is equal to d star, then
maximum of CI.
optimal lambda has this property. So if, let's write it out in simple language. If 1 minus t over b CID star is strictly greater than 0 for any reason, you want to set lambda I to 0, right? And if for any reason this is 0, then it doesn't matter. So you can pick any lambda star essentially, right? So let's say I just pick lambda star equal to 1. So one thing I want to point out is that means there always exists an optimal solution where you can normalize lambda by any scalar, any positive scalar. So if you give me any optimal solution of the dual and I multiply that by some number, it's going to remain optimal. Therefore, without loss of opportunity, I can assume that, so because of that, without loss of opportunity, I'm going to assume lambda star, or in general, this optimization problem, these are probability distributions over the D resources for a reason that we'll see. I assume lambda star is in D-dimensional simplex, or in general, always think of lambdas to be distributions. All right. This is without loss of opportunity. I can add that to the min-max problem, doesn't change the optimal solution.
But if you do this, is D star still optimal with respect to the Lagrangian relaxation? So given your lambda star, is D star is still the optimal solution to the Lagrangian relaxation?
There exists a lambda with this solution for which the D star is going to be optimal solution. That's your question. So basically, right. So I guess what I'm saying is that I can add this constraint to the min-max, and it doesn't change the value of the gain. It doesn't also change the D star, but that doesn't mean that if you remove this constraint and look at the pair D star lambda star that is optimal, the same pair is going to be optimal here as well. Because it might be the case that the lambda that you started with had summation lambda not equal to 1. But if you start from an optimal solution here, let the norm 1 to be equal to 1, by normalization there is going to be an optimal solution in the min-max problem when the constraint is there. Therefore, for any D star, this dual is going to be optimal. Maybe that was a long version of a yes to your question. So I think the answer to your question is in some sense yes, meaning that suppose D star and lambda star 1 are the optimum solution for the original program. Then I claim D star and lambda star 2 are going to be optimum solution for the second program when you add the simplex constraint, where you can, without loss of opportunity, imagine that lambda star 2 is equal to lambda star 1 divided by norm 1 of lambda star. That's what I'm trying to say. Therefore, if you start with this solution as your dual, then the same D star is going to be the optimal solution.
Shouldn't the rewards matter? The scale of R and lambda should somehow be, if lambda is like the shadow price of constraints, right? Somehow the value of reward should tell you what lambda should.
I have constant 1 here.
Still, right? I mean, so that is normalizing the constraints. So like,
Does that make?
maybe. So the sum of lambdas need not be 1.
I mean, the sum of lambdas is in your control. It can be anything.
Maybe I'll just wait.
Yeah. You can chat about it. All right, so adding this constraint is not gonna change the solution of the game. And let's actually add that, and then you start seeing a kind of interesting interpretation of the Lagrangian function. Let me put here. So I'm gonna define what I call the Lagrangian gain. Lagrangian gain. So what's the Lagrangian gain? So I have two players. Player one, primal player. Picks an arm. Then we have a dual player who picks the resource. They can randomize, so that means the primal player can pick a distribution over arms and the dual player can pick a distribution over resources. So if they go with mixed strategies, I'm gonna use D as the mixed strategy of primal player. I'm gonna use lambda as the mixed strategy of the dual player. So these are mixed strategies. So we have a payoff, lambda A and I this time. So lambda A and I is defined to be basically R of A, just one R, plus 1 minus so 1 minus T over B times the C I of A. So it is a bi-matrix game where the payoffs are defined in this way. So the primal player is the max player is trying to maximize the payoff. The dual player is trying to minimize the payoffs. Okay. So this defines what is also known as a zero-sum game, right? So you have two players, the payoff of one player is in some sense the minus payoff of the other player. So think of the Lagrangian as the reward of player one, then it plays the role of the cost of player two. So one is a reward maximum and the other one is a cost minimizer. And now they play a simultaneous game, meaning that player one goes with the distribution D over the arm, and player two goes with the distribution lambda over the resources. And given two distributions, then the expected value of the lambda A and I, if A is realized from B and I is realized from lambda, is going to be equal to the L of D and lambda that we had before, which is equal to R of D plus 1 minus T over D times Ci of D. Okay.
So can a dual player sort of play a null resource, or he has to pick one at least?
Good question. Yeah, I don't think the dual player needs to play a null resource.
So lambdas do sum to one. It's not like then can sum does do is equal to one.
Okay. All right, so now think of this game as now a repeated version. What would be the repeated version? So in the repeated version, the private player and dual player are playing this game. So now I'm gonna go to the repeated. And for a reason that you'll see, I'm gonna call it a stochastic Lagrangian game. So in this version, two players a sequence of zero-sum games where at time t, the payoff of the game, some LT of A and I, and we know, so think of LT of A and I as a random variable, meaning that, hey, these guys are playing some game, condition on the history at each time, there will be a realization of the payoff vector at time t, let's call that LT. So they play this random game at time t, given the history, and you know that the expectation of LT, A and I, let's say condition on the past. In fact, we don't even need the condition. Let's say the expectation of LT and I is equal to some fixed L of A and I as before. So this game was a one-shot game. This is a repeated game. The property it has is the same game, almost the same game is repeating over time. I say almost because you have a random payoff matrix at each time, where an expectation matches the fixed payoff matrix L. Okay. So now, good. So now here, as a one-shot game, one can study the Nash equilibrium. So the Nash equilibrium of this game is the one that we have on the right, right? So we say D star and lambda star is a pair of mixed Nash equilibrium, P pair of mixed Nash equilibrium for this game. If and only if we know the max over D, mean over lambda, L of D and lambda is equal to the mean over lambda, max over D, L of D and lambda is equal to the L of D star and lambda star. All right. Now we want to prove a claim. So claim is actually quite important. So in the repeated version, primal player runs an online learning algorithm. I'm going to say in a second what kind of online learning. Run an online learning algorithm, and dual player also runs another online learning algorithm. At high level, the claim is saying that if that happens, then they converge to a Nash equilibrium. Of the expected gain. Which has the matrix L, A, and I. Okay? So let's try to formalize this claim. All right, so imagine I'm the primal player on a some time t. There's also the dual player. So I play arm AT, and then the dual player plays resource IT. Okay, good. So then based on the arm that they have picked, an outcome is going to be realized. Right? So primal picks AT. Therefore, we'll have an outcome, which is going to be, if you remember, RT of AT, and then CT1 AT all the way to CTD AT. And then based on the strategy of player 2, so this is the dual player. We'll have L of t to be equal to L of t of AT and IT to be equal to basically that function over there. But when you replace R of A with RT, I'm going to have RT of AT here plus 1 minus T over B CTI of AT. So this is going to be the payoff for primal. So this is going to be the reward of primal. And it's going to be the cost of the dual player. So they incur this gain and cost. Okay. And now thinking about an algorithm who is actually playing in the position of both the primal player and dual player, what kind of feedback does the primal player receive? So the primal player picks AT, the other player picks IT, and then the game ends. At the end of that round, gets to see the reward. So then the primal player only gets to see the reward of that. Think of the game from the perspective of the primal player. I don't care about the dual player. I'm playing and I'm basically making decision in an online learning problem where I'm putting arms, and then there is nature, including the dual player who are deciding what reward do I get at each time. So the reward I get at time t, if I play arm AT, is going to be equal to LT AT IT. So IT comes from the nature that includes the dual player. But from my perspective, this is the reward I get to see. And I don't get to see the reward of other arms. So I only get to see the reward of the one arm that I have. So therefore, this primal player essentially receives the bandit feedback. And that's the reward of the one arm that he has. LT, IT, AT. Yes.
Are we still thinking about resource capacity and stuff, or are we kind of like?
No, we
kind of
just
set for now?
ignore that because we Lagrangify that, and we know if we play that Nash equilibrium, then the expectation of resources are going to be used up to the capacity in expectation. But good question. Yeah.
IT is independent of AT, yeah?
No, so that's a great question. So there are two views. One is like there are two strategic players that are competing against each other. But in fact, in our algorithm design framework, I'm gonna run an online learning algorithm for the primal and run an online learning algorithm for the dual. So in that sense, AT and IT are gonna be decided by the same entity, and that entity looks at the history and therefore makes a decision about AT and IT. But I mean, I don't need to be worried about whether they are dependent or independent.
Because in that game, they were playing the game concurrently, so
yeah, so
no one sees the other player.
Right. So basically, that's true. So they're playing. So in the two-player zero-sum game version, two players are playing simultaneously, and each of them is running, let's say, an online learning algorithm, and then the game is played. They get to see the reward and let's say the action of the other player at the end of that round, and then game goes to the next round. So this is the repeated game where two players are running an online learning algorithm. In my version, even though that's one interpretation of what's happening, another interpretation is really like the primal player is me, the dual player is also me. I'm going to pick an action AT by running one iteration of the online learning algorithm corresponding to the primal player that tells me, hey, pull this arm. Now I pull this arm. I also give a query to the dual player to tell me which resource should I play, and then I play that resource. Then I get to see how much payoff I have and give the corresponding feedback to both the online learning algorithm for the primal player and the dual player. But the point,
the condition and the history, they would be independent. Yeah.
Condition and the history, they would be independent. Well, yes, in some sense, yes, because the two online learning algorithms I'm using, condition and the history, they would be independent. The condition is the two online learning algorithms that I'm using, they have different sources of randomness. And therefore, AT and IT are going to be independent. But only condition the history. If I include the history, they're going to be highly correlated. But that doesn't matter, it's not going to change it. All right, so one thing I want to mention that, so this is going to be the payoff that the primal player receives, and it's going to be the cost that the dual player incurs. The primal player gets to see the reward of only the one arm that she has pulled. But then the funny part is the dual player actually has access to full information. Why is that? Because, you know, at the end of each round, when you get to see the outcome, you have the reward for arm AT and all the consumptions for all the different resources. Therefore, you can say, hey, LT of AT and some resource I, not the one resource that have been paid by the dual player, any other resource is going to be equal to RTAT plus 1 minus T over B, C, T, I, AT. And you can do that for any resource. So basically, by the outcome that you get to see in the bandit with knapsack in each round, each of the two players can get some sort of feedback for the player one, primal player. The feedback is going to be bandit feedback. The player can only get to see the payoff of the action that she has played. But for the other player, the dual player can actually simulate the payoff that she could receive by playing other resources as well. Yes.
And no one observes this whole vector OT.
Both of them, they know the vector OT, right? So this is, so again, imagine that eventually I'm going to use the primal player and dual player in one algorithm together. So after you put an arm, the outcome is going to be revealed. So you get to see both the rewards for the arm that you pulled and all the consumptions. But from this information, from the perspective of the primal player, the only information you can get is the payoff of the one arm you have pulled. Like for example, I cannot simulate the payoff of arm A if the other player has been playing IT, if A is not equal to 8. But then the dual player has the luxury of actually simulating other resources and see what would be the payoff, because you get to see the consumption for every single resource, not only for the one resource that the dual player. Yes.
The reason here is that the primal player can't actually see IT. Don't know what is the IT. Because if it knows, it can add the difference between the cost.
No, absolutely. Yeah. So in fact, again, in the game version, you kind of imagine that from the perspective of the primal player, I don't care how does the other player play. I find a sequence of actions so that it's actually a good sequence of actions. But every time that I try an action, every time I pick an arm, based on the other player's action, I get to see a reward. I don't see the reward. I don't see the action of the other player, but I get to see the payoff I get. But then the catch is in this way of, well, so in the game version, you don't get to see the action of the other player. But in the bandit with knapsack, when you're designing an algorithm and you're just running this game internally, I know what is IT. But the information about IT is not going to be helpful for the primal player to make any better decision than the one that she's already making. Is it clear what's going on here? So we have, we are in the bandit with knapsack system. And then the way that we interpret that is, there is a repeated zero-sum game that is played over time. And at each time, the payoff of the game is changing, but the expectation remains the same. There are two players, a primal player and a dual player, that are playing in this stochastic repeated zero-sum game. They are running online learning algorithms, adversarial online learning algorithms, one with bandit feedback and the other player with full information feedback. Yes.
So if all the CIs are different, the primal could technically like figure out what I was told, right?
If the CIs are different, then if the CIs are different, then the primal could figure out what I pulled, sure.
After he observes the reward.
But even if primal knows what I have been pulled, that doesn't help him to simulate the cost, because you don't get to see the reward of other arms.
Are you saying it's not useful at all? Like now you're
No,
for the
not
future
useful
of
at all.
like,
So let's say you're a primal player, because here actually you know what is the action of the other player. Eventually I'm one entity who is running both of the algorithms together. Let's say I'm the primal player and I get to see what is IT. But then how am I going to know the payoff for another arm?
well, you might not know the payoff, but at least you have, your reward is not just payoff, right? It's also coming from like the cost. And if you like know one of the arms.
So wait a second, so let's do that. So let's say I'm going to find the payoff of another arm. So let's write it down.
Understand that.
So the payoff of another arm A is going to be equal to RTA plus 1 minus T over B CT ITA. So the issue is, once you change the arm, both RT and CT change, and you don't know these two quantities. But for the dual player, if you want to get to see the cost for different options of the resource, you have to just change R, remaining A the same, and that is the type of information that you have.
But these CTs are also, CTIs are also like stochastic, right? We're kind of like learning about them as well as we go along, or no?
Well, so you get to see the outcome. So you get to see the outcome, therefore you get to see a sample from these things. Let me see. Okay.
I guess my point is that like as you go along, you kind of like are learning about the distribution of like the of action one on like I don't know resource one, etc. And so like would it not be helpful at all to know some distribution on like what your opponent or what the adversary is likely to pull, like the arm that's like likely to charge you with?
In fact, you actually you are the algorithm who is running both of the primal online learning algorithm, the dual online learning algorithm. So if you want to know what is the action that has been played by a dual player, just like look at what's action that online algorithm has sampled from, right? So if you know AT and IT, the sequence of AT and IT as they are generated. The part is, even if you know the sequence of AT-IT, from the perspective of the primal player who cares about the loss for different arms, at some time when you pull one particular arm, you cannot simulate the reward of different arms for the current IT, even if you know the current IT. Because the only outcome that you get to see is the outcome corresponding to the arm that you have. But then from the perspective of dual player, fixing AT, the dual player can simulate the cost for different resources, because once you change I, only you have to plug a different consumption for another resource in this part of the equation. So therefore, dual player receives full information feedback, but the primal player only receives bandit feedback. Okay? Is it clear?
Is there a reason we couldn't pick the strategy space for the dual player as a lambda itself? Why did we have to do it one constraint, right? Because you could just play a lambda t, and we can just say, okay, I observe lambda t, they just get L of a t comma lambda t as the feedback. That would work, right? It's like bandit linear for expert convex linear optimization, OLO essentially is the dual guys. That would also work, I guess. He's not losing too much by just playing one resource essentially is what I'm saying. could have played a lambda
Which
t.
part are you changing? I'm trying.
So the dual player plays instead of 1i, he plays a lambda t. And he gets the feedback which is L of at comma lambda.
No, but
t.
you get an unbiased estimator for, so you don't get to see.
You just get the mean. I mean, because that's anyway what he's getting, because you're giving him feedback for every arm. So he can also play a lambda and get the feedback for lambda, right?
Right, but you can plug that lambda to be the points mass on each of the resources, and you even get that information.
No, so you'll get the following. You'll get RTA plus summation lambda TI and then whatever you have there.
That's true.
So that will be the feedback he gets as the dual player.
But I'm getting better feedback than that. I'm actually getting this number for any I.
I see.
No, I see. So yeah, that's true.
So the dual, so here the dual player is randomizing, by the way.
Yes,
So,
yes.
so because I'm running an online learning algorithm with full information as a dual player, let's say I'm using hash, so still I'm randomizing, I'm picking a distribution of arms. Therefore, the expected cost I get is exactly the one that you mentioned. But the feedback that you receive is very powerful because you can, by just like looking at the outcome, you can form this function for all different eyes and get to see how much cost you get for different resources that are available. I mean, it's actually essential in the final regret bound that this player has full information and only the other player has feedback information. Okay. So good. Now, given this interpretation, let's actually write down the algorithm that we are kind of suggesting.
Let me ask you a quick question.
Yes.
Why did those parties actually observe that second to middle?
There is really not both parties. Let me actually write down the algorithm and then answer your question. Even though there is a game interpretation, it's just some interpretation. In fact, there is one algorithm with running primal player and dual player. Let me write it down and then it's going to be clear. So this is the one algorithm that you run eventually. So the bandit with knapsack algorithm. Okay. For time t equals to 1, 2, 3, all the way to the stopping, and we already know what is the criteria for stopping. Either you run out of time or you run out of one of these. Primal player goes first in some sense. It picks arm 18. In fact, you have an online learning algorithm for this. So you send the query to the online learning algorithm primal player. Based on the feedback that he has received so far, it's going to give you an arm. So suggest the arm 18. Bandit with knapsack algorithm selects arm 18. That means this is going to be the arm that you select. Now this is the part that you receive the feedback. Outcome OT, which is equal to RT of 18, together with all the consumptions corresponding to this arm. The derivatives. Okay. I'm not even, I haven't yet called the dual player. Okay, now, I asked the dual player to play an arm. So dual player picks a resource I of t. Right. Now you have to form a feedback for each of the primal player online learning algorithm and the dual player online learning algorithm. the construct the feedback. So construct feedbacks given the information that you have, which is AT, IT, and OT. Given AT, IT, and OT. So what is the feedback for the primal player? It's going to be a bandit feedback. Which is basically the the reward that he gets by playing on 18 this game against the other. And cannot actually simulate the reward that you could get if you was playing another one. Because for that, you actually need to play another arm, and you don't have the outcome corresponding to those. You only have outcome corresponding to the one arm that you have. And then for the dual player, I have the full information feedback. Which is the LT of AT and I for all i's in P. And the definition of these two functions is clear. So LT A and I, AT and I, we should think of it as RT AT plus 1 minus T over E CT I AT. That's the entire output. Did it answer your question to some extent? So even though, in fact, there is a repeated game interpretation of what's happening between the primal player and dual player, but I'm a supervisor of these two, so I can tell them how to communicate with each other, so on and so forth. But I'm not using that much communication between the primal player and dual player. I actually let them independently make a decision. I just give them the appropriate feedback that they need in an online learning problem where they pick actions. One of them is picking arms, the other one is picking resources, one is trying to maximize the reward, the other one is trying to minimize. And you should really think of it as an adversarial online learning problem. Because I don't know what is the other player doing. Even though there is a distribution in the input in this problem, but when you think about these two players, from the perspective of the primal player, I have no idea what is the other player doing. And therefore, I'm running an adversarial online learning app that has low regret with respect to the best fixed decision in hindsight, from my perspective. And for the dual player sake, is it clear? This is actually very essential. Understanding what's going on. That as a primal player, I don't want to add any assumption on the structure of the reward. And as a dual player, I don't want to add any assumption on the structure of the cost. Because the structure of the reward and cost across time essentially is highly correlated. That depends on how the other player is playing. So even though as a primal player, I might be able to see the action of the other player, but it would be hard to argue about that. So I make no assumption on the sequence of reward that I get to see as one of these players. Okay, and you will see why the adversarial online learning regret is going to help you to complete the analysis of the algorithm.
So that since the dual guy has a lambda t, right, from which he's randomized, we could just give the primal guy feedback of the entire lambda. So that that's what I was maybe trying to say earlier.
The primal guy feedback of
The full lambda, just the LT of AT comma lambda. We could help him a bit more, right?
Sure. So you could give this feedback to the primal player, but how does it help that player?
Because he just doesn't observe one like randomized. So yeah, so what he really cares about the L of A comma lambda, that would help him more to get the right distribution T.
I think what he really cares about is what would be his payoff if the other player is playing IT. He doesn't care about if the other player is playing another resource.
Why it is not included? Maybe he can use that information.
Actually, in this algorithm structure, this is not what the primal player is interested in. So the primal player is interested to be basically competitive against the average play of the.
That's what I'm saying. If you give him lambda feedback, it will help. He'll get exactly the average feedback, right? So it might help him. But I'm okay. We can wait. I don't think that may be that crucial for the regret analysis.
I guess essentially we want to learn the correct lambda as soon as possible.
For sure, yeah. So the dual player is trying to find the correct lambda, and the primal player is trying to find the correct d. That's what's going to happen. So basically, they are actually converging to the Nash equivalent of this game. I'm going to show it next. Yeah. So the role of the primal player is really finding the d, and dual player is helping the primal player in that for that objective by learning the lambda. Right.
Will you tell us how they're gonna update their d and lambdas? Or not?
Their d and lambda. No, so we are going to use online learning algorithms for that purpose in a black box fashion. We already learned how to do adversarial online learning for full information and bandit information in the previous course. So basically, the primal player is running hedge, the multiplicative weight update, and the dual player is running x3. But that would be for the next part. Let me continue on. Show you how to basically I'm gonna say something along the lines of what you just said.
Can you please not erase that part?
This one?
Yeah.
The algorithm? Sure. All right. So now assume primal player runs the bandit information adversarial online learning algorithm for a reward maximization problem, where the rewards are essentially equal to LTA and IT, for T from 1 to capital T. So these are the rewards for different arms. I'm looking at the game from the perspective of primal player, who is picking an arm, fixing the strategy of the dual player, the sequence I1 to IT. So that defines an instance of a multi-arm bandit problem where if you pull arm A, your reward is going to be equal to LTA IT at time T. So some adversarial online learning problem. So we're going to run. Okay, so now, as part of the assumption, we assume the regret with respect to the best arm in hindsight for the primal player is bounded by some function. So I'm going to say that basically 1/t, let me use accumulated regret. So summation over t from 1 to capital T, LT, AT, which is going to be the reward that the algorithm gets, is going to be equal to the maximum reward that you could get, max over all A's, minus some particular regret of primal at time t. That's the definition. Okay. And whatever this function is, it depends on the regret performance of adversarial online learning algorithms with bandit feedback. We are gonna fix that later. Also, the dual player wants the full information adversarial online learning. For the sequence of costs, which are equal to LT, AT, and I for different resources that this player could play at time t equal to 1. And then because of the regret currency of this algorithm, we say, well, summation T from 1 to capital T, LT, AT, IT, which is the total cost that the dual player accumulates, is going to be equal to the minimum I in D sum over all the T's, LT of AT and I, this time plus some regret bounds for the dual player at type T. And somehow, because of the guarantees of these two online learning algorithms, we know this is sublinear in T, this is sublinear in T. Later, we're going to use the actual functional forms that we know about these two problems. But for now, let's just leave them as RP of T and RD of T. Is it clear how we are thinking about the two online learning problems that are related to the algorithm? If you have any questions, right? Yes.
If the max and min are equal because of the strangulability.
No, they're not equal.
So how did you drive the left-hand
These two
side?
functions are different. The left-hand sides are the same. These two are different. These two are different. Okay. This is just the definition of regret for these algorithms.
This is like best, like fixed course, right?
Correct. Yeah, because it is an adversarial online learning algorithm, I know basically the reward I accumulate is close enough to the best fixed in hindsight action up to the regret amounts that I accumulate. And then same as the cost minimization problem, you have to look at the best fixed resource in hindsight. It's a minimization problem, so this is why we have a min here, we have max.
So is A an action or a simplex in delta K?
Here I'm thinking about
I'm talking about
an actual R, not
I'm talking about the first definition of the primal regret.
Oh, right, you're right. I think this is enough to. I mean, it's this. It gives you the same thing because you're maximizing, but it is unnecessary. So you're absolutely right that there will be one arm. Even though you could maximize over the distribution over arm, but there is always one arm that is the best fixed arm size. If there are multiple arms, then any mixed strategy over them is going to be also optimal. But I don't care about that. Just pick one arm. Okay, good. So now let's see why, if we run these two algorithms, then we're going to get close to lambda star d star. Basically, why we are gonna converge to a Nash equation. So I'm gonna look at the first one. So we will have some t from 1 to capital T. Let me actually divide everything by 1 over t. You will see in a second why this is the case. LT, AT, IT. Okay, so let's say I think the argmax here is some arm A star, and then the argument here is some resource I star. So this is going to be equal to 1 over t summation t in t LT A star IT minus over t. Okay. Let me also define two mixed strategies. So we are going to look at AT bar and IT bar. So what is AT bar? So this is basically I pick AT with probability 1 over t. And this is saying IT with probability 1 over t. These are two mixed strategies for the one-shot version. So if I have the sequence A1 to A capital T, I can say the average distribution is going to be pick each of them with probability 1 over t. Basically, pick one time from that random, look at the arm in that time, and play that one. And the same for the sequence I1 to I capital T. It's just like some definition. So I'm going to call them average plays. And claim this is a maximization, right? So this is going to be greater or equal than 1 over t summation over all t's LT of a double star IT minus RP of t. And what is A double star? So A double star is the best strategy against the average play, is the best strategy of the primal player against the average play of the dual player. So it's going to be the max over all A's. I'm looking at the expected gain this time. Yes, I'm looking at the expected gain. And I assume the second player is playing this average strategy, the one that I defined down. That's argmax. That's the argmax. Okay, so by definition of ASR, it's going to be better than any other analysis. Yes.
Can you please repeat the definition
I
of
couldn't hear you.
Can you please repeat the definition of average?
Oh yeah, so this is a repeated game. Now let's switch to a one-shot game for a second. So given the sequence A1 to A capital T, I'm going to define a mixed strategy in that one-shot. It's called the average play. How is it defined? So given the sequence A1 to A capital T, I'm going to play AT with probability 1 over capital T. There are T different.
Sum of probabilities wouldn't be 1.
We have capital T
Don't
number
we
of
have-
arms.
You have n number of arms, so it would be n over 2.
No. So I'm fixing a sequence A1 to A capital, the actual sequence that is played by my algorithm. Given that sequence, I define the average play to be a mixed strategy over KR, I'm gonna play AT with bounty 1 over T.
Oh, I see.
Like let's say I'm pulling on 1, then 2, then 1, then 3, then 4. Then the average play is with probability 1 over 7. This one,
That's
the other one over 7, this one.
Yeah, it's 4 over 7, like pick the first arm.
Right.
You mean that?
Yeah, but with probability 4 over 7, pick 1. And then with probability 1 over 7, pick 2, 1 over 7, 3, 1 over 7.
So for the average play, you need the whole play of the whole
Correct.
play.
Yeah, yeah. This is not something I'm gonna use. I'm gonna use it in the analysis, but not in the actual game. The reason I'm using the average play, the reason I'm using AWSO is because I'm gonna move from the stochastic game to the expected game. That's the reason. And you will see that in a second. But this line is clear, right? Why from the first line we can get to the second line. Because A star is the best fixed in hindsight strategy for this sequence. Therefore, it is going to be better than another strategy A now. So yes.
Is the Lagrangian function linear in I? So
What is linear in I?
so if this is the case, is A star equal to A double star?
No, but you have this T, so these are random variables. So change. So these are random variables. So in some sense, A star is actually a random variable. A is not a random variable. So even saying that A star and A double star are equal to 0 is just wrong. Right? So you have a repeated stochastic game. At each time you have a Lagrangian, random Lagrangian as the payoff of the game, which in expectation is equal to this quantity. And given all those realizations, there is one arm that is maximizing, that's A star. However, A double star is the one that is the best arm for the expected game when you play against the average play of the dual player. So these two are different. So this is actually a random variable, this is not.
I bar T is also a random variable.
Condition on I bar T, this is still a random variable, this is not. So they have two different distributions.
So what do you think is this L of A comma I bar T is not the same as this summation T LT AIT? Think
No. No. So but if there was no T, you were right.
Oh, I see.
If there was no T, you were right, and I'm going to use that. Okay, so this part is just like using this property, but let's actually follow with the idea that Varun and Chen have. So I'm gonna try to move from LT to L. So this is gonna be equal to 1 over T, T in T, L of A double star and IT minus RP T divided by T plus sum over all the T's, and then there is a 1 over T also. So we'll have a martingale here. M1 of T and M1 of T is defined to be, let me use the negative sign, just makes it easier. So M1 of T is defined to be, I believe, L of A double star IT minus LT of A double star IT. This is the definition. And expectation of M1 of T condition on the history up to time T minus 1 is essentially equal to 0. So therefore, this is defining the martingale response when you add up these differences. Okay. Now, we don't have a notation for the value of the game. But we write here, so we have V star to be equal to lambda D star and lambda star, which is also equal to opt LP by a strong duality. So I claim that this is actually greater or equal than V star. And let's see why. In order to show this, you actually have to use the exact value rest. So this summation is equal to L at A double star when the second player is playing the average play because of the linearity of L. And now think about that. So the second player is playing the average play, and then the first player, so imagine the second player goes first, picks the average player, second player goes first, picks the average play. The first player goes second, picks the best response, which is A double star. Then you get this value. But we know the best strategy of the first player, even if the first player goes, the best strategy of the second player, if she goes first, is going to be playing with lambda star. Meaning that among all the mixed strategies that I have as a second player, if I pick lambda star, and then the first player picks the best response, I have the smallest value of the game, and the minimizer. So switching from the average play to lambda star, and then letting the other player play best response only brings down the value. And if I play the equilibrium strategy, lambda star, as the second player, and the other player plays the best response, this is going to be exactly equal to the value of I'm assuming that you're familiar with zero-sum games to some extent. Meaning that there are two players, if I go first, the other player goes second, it's the same as if the other player goes first and I go second. That's the meaning of the min-max that we have written down there. If you have paid attention, we could switch the min and max and nothing was different. So this is basically meaning that if the second player goes first and then the first player goes second, then if the first player goes with the equilibrium strategy and the second player and the first player who is going second plays with the best response, then the value would be equal to the equilibrium value. Is it clear how we get from this line to this line?
No.
Okay. In a zero-sum game, it doesn't matter which player goes.
The things you are saying. Can you write which is equal, which is greater than? You are.
Okay, so I guess I'm trying to say L of A double star and I T bar is greater or equal than the max over all the arms, L of A and lambda star. And this is equal to this. Suppose you want to solve this game, you want to attend this game as a second player. You know, if you go with the equilibrium strategy and the other player plays the best response in response to your mixed strategy, then the value is going to be equal to the value.
Because of the definition of equilibrium, D star was the best response for lambda star.
Because of the min-max property, sometimes it doesn't matter whether the simultaneous game is equivalent to the game in which either of the players goes first and the other one goes second. It's because of that. Equilibrium comes from the simultaneous version. But if you also give a sequence, meaning that one player goes first, the other one goes second, the second player always plays best response, right? It's the best thing that player can do. But still, that doesn't change the value of the game. Therefore, if one player goes with the equilibrium strategy and the other player plays the best response, still the value you get is going to be equal to the equilibrium value. I'm using that property here.
Best response is the equilibrium, is the
No,
D star.
best response is best response. equilibrium is a pair of strategies. So ds star and lambda star
Yeah, I mean D star. D star isn't the best response.
is the best response to lambda star. But it's not the only best response to lambda star. There might be, yeah, so basically another way of saying that is that if I know ds star lambda star is equilibrium, then one choice here would be randomizing over all of the possible best responses, and ds star has that property. Sure, if that helps, this thing. This step is trivial. I think the one that is a little bit tricky is here. This is saying that, if I'm solving the game as the player who is going first, I'm always better with lambdas. Imagine I'm second player, I'm trying to minimize. It's a Stackelberg game, so I know the second player, basically the one who goes next, is always doing best response. Among all the mixed strategy, lambda is the best one that I should pick. It minimizes my Stackelberg game payoff, Stackelberg game cost, because I cost minutes. And therefore, so compare two choices, lambda star with the average play, lambda star is beating average play.
Yeah.
If the second player, the player who goes second,
But that player sees what the first player is playing.
Yeah.
So you mean the best response doesn't depend on the first player, even
It
though
does.
he's not playing?
it does. It does. What I'm saying is, a Stackelberg game is a game that I go first, the other player sees my action and picks the best response. In the Stackelberg view of a simultaneous two-player game, the best strategy that the first player has is the equilibrium strategy. Why? Because, well, so it comes from the definition of the equilibrium. Let me ask you the following question. Suppose I know the other player is going to do best response, whatever, no matter what they do. Is going to do the best response with respect to my action. Then what would be the strategy that minimizes your cost? I claim it is the equilibrium strategy.
Oh, you mean lambda star is the first player?
Yeah,
The one who
let's call them primal-dual player. So lambda star is the equilibrium strategy of the dual player. Assume dual player goes first. So
now
he knows that the primal player is going to play best response. I'm playing among all the mixed strategies that dual player can play.
lambda star
Lambda star is the best one. It's the one that minimizes their cost.
Yeah, again by that definition of min, max, max,
Exactly.
min. Okay.
So therefore, this is not less than. But it is important that the other play is not just like, if it was the same action, then you couldn't say it.
Yeah, the best action.
It should be the best action, should be the best response. I hope it is clear for others. But maybe it's a little bit fast. Anyways, so we have this inequality. And in fact, I'm not going to write it down, but if you exactly use the same logic for the dual player, then you can say 1 over t summation t from 1 to t lt at it is going to be at most v star plus, so this is for primal player, this is going to be for the dual player. So for the dual player, I can say, I can repeat the same calculations. The average cost is going to be at most v star plus r dt divided by t plus 1 over t summation t in t of m2t, where this time m2t is going to be another martingale. I think it's going to be something like L of at I double star, and I double star is defined the same way, but for the second player, minus LT of AT and I double star. And again, the expectation of M2T conditional history
is equal to.
It's a mark. All right. We are very close to the final analysis, and let me actually. Okay, so one thing I want to mention is that, well, so this is actually saying we are close to, so if assuming that this term is also pretty small, then for both players, the cost is a zero sum game, right? So the cost of one player is equal to the reward of the other player, and it is actually fairly close to V star. It is upper bounded by V star plus something is small, and it's lower bounded by V star minus something is small. So as time goes on, they actually converge to the equilibrium, the D star lambda star, and the equilibrium is going to be the one that gives you the maximum reward. So intuitively speaking, that's the case. Then we write down a theorem, and then we try to prove that. Can I erase this one? So this is the theorem that we are trying to prove. We have almost proved it, but let's try to finish. So the bandit with knapsack algorithm as they obtains the regret bound of, so opt LP minus the reward of the bandit with knapsack algorithm will be upper bounded by order T over B times square root TK log BT divided by delta is probability 1 minus delta. It's actually a high probability regret bound. Yeah, if P is a small, this is not going to be a good bound, but if P is large enough, then it's going to be order a square. So this is basically O tilde of a square root TK when P is big omega T. That's what this bound is about. So there is another theorem, I'm going to write it down, but I'm not going to prove that. So theorem 1, theorem 2. In fact, we can improve this analysis by modifying the algorithm a little bit. I'm not going to show you how. So there is a slight modification. And it becomes like algorithm. That obtains. So it obtains actually a better regret bound than expectation. So opt LP minus expectation of the reward of bandit with knapsack tilde, that's the modified version, would be at most O tilde of a square root K opt LP plus opt LP times the square root K over B. Kind of a weird bound. but this is information theoretical outcome for this problem. It's the best thing that one can do. And in particular, this is going to be a better bound, for example, if the improvement. So this is better if opt is a smaller than the square root p times t. So in a regime where p is still large, but not super large, you can get improved. And when p is a small, there is no hope for getting any meaningful result. Okay. So I'm gonna use the current analysis that we have in order to prove theorem 1. And in fact, the rest of the proof is not that hard. Any questions about the statement of the two theorems? So the first one is a high probability bound, the second one is an expectation bound. Yes.
So essentially, we want to learn lambda as fast as possible. So if I consider the very simple policy, I first use the TK theories to explore, and then I observe the outcomes, and I use the empirical LP to learn lambda.
Mm-hmm. Yeah, great. There is a version of the exploration first, exploitation next that works, and you can get t to the 2/3 to the bounds.
Okay. Yes.
If you want to get the square root regret, you have to kind of learn the duals over time.
I guess the whole algorithm even works for non-stationary setting.
Oh. So the same algorithm for the non-stationary setting will give you order log t competitive ratio. It's not going to be a regret bound. There is a recent paper, adversarial bandit with knapsack. So you mean adversarial in the sense that the sequence of outcomes?
No, I mean non-stationary distribution, but the distribution is not known.
But if it is arbitrary non-stationary,
Okay.
then adversarial is going to be included in your definition. So if there is really no controlling over how the distribution changes, the adversarial setting, then you cannot get bounded regret. But then you can show you can get order log t competitive. The ratio can be as well as order log.
We don't need to change the algorithm at all.
There is a slight modification, but essentially, so the two online learning algorithms that you pick, one of them should be mirror descent for the full information version, but rather than that, you don't need to change anything. It should be mirror descent because of a technical reason. Maybe there is a way to get around that as well. Which is, by the way, the star of the show in our next lecture. So we're going to talk about online mirror descent, how it's going to help with online learning with adversarial approach. Okay, so let me try to finish the analysis. So the rest is just a bunch of concentration inequalities. And the second analysis is going to use the Bernstein inequality that we mentioned in the dynamic pricing with limited supply lecture, but the simpler theorem number 1 only needs Azumal. So in terms of concentrations, we are not going to use any fancy. So lemma suppose our algorithm terminates at time tau. Basically, tau is equal to the stopping tau. So tau is basically the earlier of the two events. Either you finish with the horizon as one of your resources, or you finish one of your actual resources. If you run out of time or you run out of any of the resources, you're gonna stop, and I call tau to be the stopping time. Then the following is true. So we're gonna have the point size reward of the algorithm to be at least tau times the average Lagrangian function at the average. Oh, let me say something. So, excuse me. Suppose at this time, suppose we run out of some resource, I. So I is the one resource that you run out. Then I'm claiming that the reward that the algorithm gets is at least tau times the Lagrangian function of the average play up to time tau, if the other is playing I. Plus t minus tau times output p minus epsilon by tau, which is something that I'm gonna decide after proof what that function should be. To be set. So this is the proof. Really, the proof is coming up with what is epsilon 18 by tau. So I'm going to start with this Lagrangian for the average play. So the Lagrangian for the average play multiplied by tau. So this is going to be equal to tau times, let's just write it down, R at the average play plus 1 minus T over B times C of I at the average play. Okay, so this is equal to tau times let me write it down and then tau minus T over B summation CT I AT Oh. Right. So this guy is basically sum over all T in tau R of a T divided by T divided by tau, essentially. And I'm moving from RAT to RTAT to connect it to the reward I get. Therefore, I have to add the summation. Well, actually, I'm subtracting. So subtracting summation for all T in tau RT minus summation T in tau or T in T minus tau or of tau bar minus summation minus T over B times summation T in tau CTI plus let me write it down there. Plus is minus. Let's see what they do. So this is by definition. From this line to this line, I just added a bunch of terms and removed a bunch of terms. Because the way to think about R of the average plane is equal to the sum of R of ATs over T in tau divided by tau. I want to connect this term. So this is kind of like the expected reward algorithm because I want to connect it to the actual reward of the algorithm because therefore I add this term and I subtract this term. Same as the cost or the consumption. Not the cost, the consumption. So this is average consumption over time 1 to a stopping time. I'm going to replace that with the actual consumption. And then I add that and subtract. So this is exactly what you have. Okay. Let's now decide what is our epsilon I tau. So this is what I call epsilon I tau. Basically, this entire thing here is the minus epsilon I tau. Now note that we know we have run out of resource I, so that means this quantity here, the summation of consumption for resource I, is actually greater than B. Therefore, we can say this is at most, and this quantity is the reward of the algorithm. So then you can say the reward of this is at most the reward of the algorithm, the reward of use BWK. So it's at most the reward of BWK, the pointwise reward of BWK, plus tau minus T, right? Because this is at most B, this is at least B, then this divided by B is at least 1, minus of that thing is at most minus T. So therefore you get these. And then actually, I'm going to call this plus. Sorry, guys. Minus. Plus. This plus epsilon I tau. And then this is at most the revenue plus the reward plus tau minus T times opt LP, simply because opt LP it is at most 1. Remember, so opt LP was just for 1 round, so it is at most of this.
Why does that time on the 0?
Yeah, because this is in expectation 0. So
that's because RT, not R.
that's RT, right? And this is also CTR. And you know, expectation of RTA is equal to R of A.
Which, if it was R of A, then it was.
Yeah, for sure, for sure. So there is this layer of, fresh randomness at each time. The way to handle that is defining these kinds of differences and then trying to use concentration bound to say that some of these differences is small. That's like tau. And now if we rearrange the terms, so the conclusion would be the reward of the bandit with knapsack algorithm is going to be at least tau times the Lagrangian in tau bar I plus t minus tau times octal p minus epsilon I. Okay, so this is the lemma. Now, what do I know about the Lagrangian pay, the average Lagrangian payoff or the Lagrangian payoff at some resource I when the primal player is going with the average play? If you remember the inequalities that I had, average play from the primal player is pretty close to the equilibrium strategy of that player. And in particular, one of the inequalities that I showed is that the Lagrangian at the average play in this case, we have Lagrangian for any I. The Lagrangian, when the first player, the primal player goes with the average play, and the second player goes with I, is always greater or equal than if the second player plays best response, which is the Lagrangian at the average play, and I had the notation I double star there. And we showed in one of the lemmas, the one that was here erased, that this is actually greater or equal than V star, the value of the gain. I don't know if I show, I showed this, but I didn't show you how to rearrange the terms. So this is at least V star minus essentially both of the primal average regret and the dual average regret. Right. Minus sum over OT tau M1 plus M2 T. This is actually what we show in that lemma. So if you look at your notes, what we showed was this term plus this term, and one of these martingale was greater or equal than V star minus V. So if you rearrange the terms, you get to this inequality. And intuitively speaking, what it says is that the average play is close to the best, is close to the equilibrium strategy for the primal player. Okay. So now, if you plug this into there, what we conclude is that the reward of the bandit with knapsack is going to be greater or equal than tau times V star Let me absorb the other terms here, and then we get back to these guys. So tau times V star plus t minus tau times octal p. And then we will have a bunch of error terms. Three sources of error. So minus. So the regret part, RP tau divided by tau plus RP tau divided by tau. We will have the martingale part, from the repeated game interpretation. This comes from the fact that this is a stochastic thing. So summation t from 1 to tau m1 plus m2 of t. And then the last part, which was this epsilon by tau that we discussed. So V star is nothing but just octal p, so these two are equal to each other. Because the value of the game is octal p. So this part will give us octal p. So really our regret comes from these three sources. One, the regret of the two online learning algorithms. Yes.
And shouldn't all those green things multiplied by tau and also the previous?
I think you're right.
And also the
You are right. So this one has already 1 over 1 tau, and it should multiply by 1 tau. Good. So this, right. So this will be fixed. I mean, okay. Not here.
Right.
So there was 1 over tau here for sure, right? And then I look at tau times this, so that gives us tau b star. So these taus cancel, this star cancels.
you also need tau time. No, it's okay.
That's when it comes as it is. Thank you. Okay, so our regret is going to be coming from the two regrets of the online learning algorithms, this epsilon part that we got at the end, and these markings. So, yeah, I think I have time to show you the concentration. So, these guys are just like coming from some book, like pick your favorite book on online convex optimization or refer to your notes from Varun's class. So RP of even t, right? So RP of tau, I claim is going to be let me do them again. Let's actually talk about the other two. That's easier. What do we know about M1 and M2? So M1 was the Martingale sequence. Expectation of M1T, basically sum of M1 is the Martingale sequence. This is the Martingale difference sequence. Expectation of M1T condition on the history was equal to 0. If you remember, the definition of M1T was the Lagrangian at one point minus the Lagrangian at another point. And the Lagrangians are between minus t over b all the way to 1. So what I'm trying to say is that the absolute value of M1t is bounded by order t over b.
Can you see why?
Right, so M1t, the definition was the difference of the two Lagrangians, right? So it was the Lagrangian at some point minus the LT at that point. And our Lagrangian functions, they have this structure. So the Lagrangian function is basically some R plus 1 minus t over b times some c, where R and c are between 0 and 1. So what is the maximum quantity that this can take? Actually, is 2. The minimum quantity it can take is when this is 0 and this is 1, so it's going to be 1 minus t over b.
So it can be 1 plus t over.
Yeah, think about the regime where b is a small event. So if b is a small, then this is going to be minus t over b. The absolute value is going to be bounded by order t over b. Okay. And then this is the mark, so now, same as M2. And in fact, if I look at M1 plus M2, I can say the same thing. Okay, so I assume you guys are familiar with Azuma. So if I look at S of t to be equal to the summation of M of t, t from 1 to t, then from the Azuma inequality, we know the probability that S of t minus 0 in absolute value is greater than some epsilon is at most 2 times e to the power minus epsilon squared divided by 2 times the sum of the absolute values on the differences squared. That would be 2 times, let's say this is tau. That would be 2 times tau times order L squared, when L is equal to order T over L. All right. So this is just for one choice of tau. Let's say I want the probability to be small so that I can eventually do a union bound over all possible taus, so that I can say with probability delta, no matter what tau I have, this inequality holds. That means I want to make this probability to be as small as delta over tau. Let's say I want to make it as small as delta over t, right? Actually, delta over t. That will give us a certain epsilon, so that means epsilon squared divided by 2 tau L squared should be at least log of t divided by delta, and therefore epsilon should be at, right. So any epsilon that you can use is an epsilon that should be at least L or order L times the square root of tau log t divided by delta. So in particular, let epsilon to be order L times the square root t log t over delta. Then you can say with probability delta over t, absolute value of S of t is at most this epsilon for any tau. And therefore, if you do a union bound, you can say, therefore, with probability at least 1 minus delta for every tau in t, I have absolute value of S of tau is smaller than order L square root t log t over delta. Here I have used union bound. For one particular tau, you know the probability that is one as delta over t. There are capital T number of taus. Therefore, the probability of bad event is going to be at most delta. The probability of good event is actually 1 minus delta. And you can say with probability 1 minus delta, the good event happened, which is the complement of this event. Absolute value of S of tau is going to be at most order L square root t log t delta. So now we have a control over this. For epsilon I tau, you can do the same thing because this is not even a marking. So you have a condition on the sequence A, you have a sum of independent random variables. So you repeat the same experiment on these guys, and that gives you a bound for this term. It has the same form. I'm not going to show you that one. So that's just exercise at home. Is it clear how to get a bound on epsilon I tau? Because even if I condition on the sequence AT, you look at the reverse, realize from one particular arm at a time, you have a sum of independent random variables on one side. Each one is bounded by 1. And the other side, you have the expectation of their summation. Because the expectation of RT is equal to R. So therefore, you can use even Chernoff bound here, but Azuma would be enough, and you get more or less the same type of bound. And if you're wondering where is this K, so far we have this T log, T over delta type of thing. Oh, and by the way, so there will be a log D because for each I and tau, you will have a bound of this form. So you want to make this bound as small as delta divided by T times D, so that you can say for every I, for every tau, this is bounded. And this is why you get a log D here. And then finally, this is the bottleneck. Let me do something quick. So let's say we didn't want to get high probability bounds. So let's say I'm just looking at the unlearning problem for a primal player. So for the primal player, solves a multi-arm bandit problem with expanded feedback. Let's say primal player is using EXP3. Actually, let's say it's using online mirror descent. As we saw in Varun's class last quarter, we know the expectation of the regrets, basic expectation of the regret of the primal, let's say, tau, would be basically order a square root. So how many arms do you have? K number of arms. So it's going to be order a square root K times essentially tau. Now, if you want to get a high probability bound, you can look at the proof of the online resistance. I'm not going to show you, but somehow in a similar fashion, you can conclude that, hey, if for every tau I can get this kind of bound, then I'm good to go. And then the rest is going to be union bound over all the rounds. And this is kind of like coming from a textbook in some sense. So we can say with probability 1 minus delta, RP of tau is going to be order the square root K times tau log of tau divided by delta. And this log tau divided by delta comes from the union. This is fairly a standard, so I'm not going to show you the details. If you are really curious, just go to the online convex optimization book of Sebastian to see how we can get high probability bound for adversarial unlearning. But I'm kind of using this result in a black hole fashion. And then the dual player, assume, is using hedge because it's a full information online learning, is using hedge or multiplication by rate of date. If that is the case, in expectation, you can say the expectation of R d tau is something like order square root. Okay, so how many choices this guy has? D choices. So it's going to be order the square root log d times tau. So tau times log d. And if you want to get a high probability bound, somehow you have to have this bound to hold for every tau, and then you have to do a union bound over all the rounds. So you can say with probability 1 minus delta r d tau for every single tau is going to be order a square root t or tau log d times t divided by that. I replace tau with t because this is just an upper bound. So long story short, the combination of all of these bounds together, so this one, the one that I didn't write down, will give you the theorem. So one thing I have to add that I think in this online learning problem, you get this figured out if the maximum reward is upper bounded by 1. But we should note that the rewards in this problem are coming from the Lagrangian function, which in principle is bounded by t over b. That will add the order t over b linear to the regress, because at the first step you have to normalize everything by the maximum reward, and then you're going to be in a world where the rewards are bounded by 1. Once you